this talk in the afternoon, I will be concentrating on another area of which has an interface with biotechnology, and that is on liquid biofuels. Now, among the various alternative sources of energy like wind energy, solar energy and so on, the biological fuels have a unique advantage or a unique place. While they are renewable in nature, they can also offer you additional benefits of waste recycling, or you can say waste remediation. They can also provide you an opportunity to provide a good quality of energy. When I say good quality, I mean many of the pollution aspects of the conventional liquid fuels, which are based on petroleum, crude petroleum, in terms of environmental emissions, could be SOx, NOx, can be minimized. And in that perspective, the biofuels as a renewable source of energy have a very important role. As a matter of fact, if you look at the organic feedstock scenario of our civilization up to about 1930, I mean just after the industrial revolution, the era of industrial revolution, the whole industry was based on coal as a source of energy, and with the coal were associated many aromatics, phenolics, and also there were some energy requirement was met by plant and animal waste. I think even in our part of the world, animal waste like cow dung was a very important source of energy as a solid fuel. During the period of 1930 to 72, a very big revolution came in the field of energy by way of petroleum processing industries. People realized the potential of crude petroleum, the crude oil so called, the black gold, which probably created a fortune for a large sector of geographical locations which have abundance of this resource, and the whole energy sector became essentially based on the geographical location. I mean certain countries, what we call as OPEC countries and all that, they become the dominant force to dictate. Now, today the scenario is that we are approaching $100 per barrel. I heard, from one of my friend while traveling from Delhi, it has already touched $98. Dollar is going down, so the price is going up, and $98 we have touched. While people were guessing in the last decade it will touch 100, now people have started guessing it will touch 150. So, I mean that is the kind of scenario which is scaring, practically scaring, and for all our activities in this century, we are dependent on energy. And actually after 72, people started realizing the environmental concern of crude petroleum. Sulfur dioxide emissions, carbon dioxide, carbon monoxide emissions, nitrous oxide emissions, they really scared people when people saw their final health problems. Also people got concerned that the crude being a fossil fuel is a limited resource. You cannot depend on it. Now, it is a question of anybody's guesswork. It may last for 50 years, it may last for 100 years, 150 years, but it is not unlimited, because the cycling rate is millions of years. So, nobody can see millions of years. We can definitely plan and for a few decades, and in that respect the crude was slightly, people got cautious about it and started looking for renewable source of energy, among which biofuels became a potential alternative. Now, first thing I think, let us for our understanding define what we mean by biofuels. The biofuels are essentially energy sources that are derived from biomass. I would like to underline the word biomass, which are renewable. I mean the biomass, when I say, I do not restrict it to any specific form of living cells, it could be plants, it could be animals, animal wastes, it could be even microbial cell mass. From any source, whatever energy we can derive is covered under biofuels, or its component as a feedstock. It could be solid briquettes. I mean, you can start with, let us say, cow dung and make in the form of briquettes after mixing with the lignocellulosic material some solid waste. It could be biogas, we are all familiar with the biogas in the gas form. It could be ethanol, it could be biodiesel. There are some typical examples. Of course, under the biofuels, you could also consider hydrogen as one of the ideal fuels, which could be derived from biological sources theoretically, if so far practically it may be still a distant view. The primary inputs that are required for these biofuels are land, know-how and solar energy, because the primary source for all biological renewable source of energy is the solar energy, because whether it is the growth of plants or growth of microbial cells, they depend on a source of energy as sunlight, and advantage is that they are renewable and environment friendly. And the major another advantage, particularly from the point of view of countries like ours, which are developing countries and whose economy is very largely agriculture based, this can provide a very variety of application areas. I mean, it can suit to variety of application sectors. We may need energy for agriculture sectors, and you can tailor your requirement of the energy using biofuels to meet that requirement. You may require it to be used for industrial purposes, it can be converted into that form. So, there is a large variety, adaptability for the scale of operation. It can work on small scales, it can work on large scale, and that is the reason why we always sometimes call it a sustainable form of energy. That means, it can sustain for a longer period, and we can look at a long period. If you look at some of the historical perspectives in terms of some numbers, on a global basis, consumption of firewood grew from 500 million meter cube per annum before First World War to 1070 million meter cube in 1950 at the end of Second World War. This was the growth of, what I am trying to emphasize by this, that our energy requirement have been very grossly increasing with time. It has never become stationary. Even today, the growth profile is exponential, is logarithmic, and that is one concern, and before becoming constant with a consequent decrease on the per capita basis. Of course, population has compensated when you calculate in the form of per capita basis, but if in absolute term it has been increasing. Until 1929, all US ethanol for fuel was produced via fermentation of grains, molasses and other carbohydrate sources before abundant petroleum supplies. I mean, before the petroleum supplies were there, the so called the gasohol, a mixture of hydrocarbons and petroleum and alcohol, the major source was fermentation. The biofuel produced by fermentation of sugars, these sugars were produced either from corn or from fermentation of molasses. With the advent of internal combustion engine and during the two world wars, fermentation alcohol made inroads into the national transport sectors, particularly in Germany, US and Brazil. I think in the period around 70s, early 70s, Brazil took a very sort of extraordinary role in deciding, because they were one of the major petroleum importing country. So, they probably took it at a political level, they took a decision that we would like to do agriculture for the sake of energy, and their whole sugarcane cultivation was aimed at producing alcohol, and essentially they had the programs. They have now different grades of petrol which contain different percentages of alcohol. So, and this became quite popular in US, Brazil and Germany. Let us look at some of the statistical figures, some of the not statistical rather numbers. What is the potential of the bioenergy? Is it large enough to meet the requirement of energy for in future to come, or is just a hypothetical situation? And if you look at the solar radiations that are incident on earth surface are of the order of 3 into 10 to the power 6 erga joules, which equals about 75 times the present proven burnt fossil fuel energy sources. 75 times. Now, this is minded, this quantity of energy is not one time energy. This energy, current fossil energy reserve is one time, whereas this is a renewable form. Every year so much of energy is incident on the earth. Obviously, we cannot convert whole of this into usable form of energy, but even if you look at the overall efficiency by photosynthesis comes out to be about average in the average form 1 to 2%. Of course, some plant may have a little more, but average photosynthetic efficiency by which it can be converted into a chemical form of energy is 1 to 2%. Even that is large enough to meet our energy requirements and on a renewable basis. That is what the message I wanted to. Now, essentially if you look at the approaches for energy production from biomass, you can cultivate specific energy crops. That means, so far our whole of agriculture is designed to meet our needs of food and fiber. People have not looked the agriculture as a source of energy, but a trend is changing. The trend is changing now. Even Government of India has been looking at cultivation of jatropha, for example, to meet our partial energy requirement. Still it is a little distant view, but probably the thinking has started. Even much earlier than that, people have planned that in our forest plantation we must keep in mind the energy farming. That means, we put a mix of planting material which give you timber as well as some energy crop. Energy crop can be fast growing, timber will be a slow growing species. So, that most of the forest plantation are aimed at timber, production of timber, but people had been planning, and in fact, there have been many efforts in countries like Canada, Sweden and some part in India, where a mixed cropping pattern in forest has been attempted, so as to provide both timber as well as energy. Then I think the third, then harvesting of natural vegetation. There are some vegetation which is naturally growing, can be cultivated, can be used as a source of energy. Finally, I think a very important source of energy can be derived from recycling of agricultural and industrial residues. Now, even if you consider the conventional agricultural form for producing our food and fiber, substantial quantity of biomass is generated as a side product, You can't afford to produce wheat without producing the wheat straw. You can't produce rice without producing the rice straw. Almost an equal volume or equal weight, rather more, is produced as a straw, which are cellulosic in nature and can be used as a source of energy. Now, subsequently these all material from all the three categories can then be converted to biomass, converted to biofuels by either of these, either by anaerobic digestion, in which the main process a carbohydrate molecule, or for that matter any organic molecule which is biodegradable, is converted to methane and carbon dioxide via organic acids, is anaerobic digestion. Fermentation, you can convert the cellulosic material to glucose and followed by conversion to alcohol by fermentation, including chemical and thermal routes by combustion, thermal gasification, and finally, I think in biodiesel, which we will talk about, transesterification. If your feedstock is oil in nature, triglycerides, you can do transesterification to get a product similar to diesel, what we call as biodiesel. If you look at the various options available to us for processing of biomass, you can go by simple method as briquetting, for which can be used for combustion to produce electricity or steam in boilers for industrial applications. You can have dry chemical processes under pyrolysis, gasification, hydrogasification, or thirdly we can have aqueous processes which are largely biological processes which are which come under the realm of biotechnology, which you can do either you can do oils, you can have ethanol, you can produce methane, and you can also produce this biomass if there is vegetable oil can be converted to biodiesel. So, these are some of the product spectrum from biomass. If you look at the availability of the residues, agro residues in India, of course, these figures are indicative. I mean, I do not claim that these are exact figures, which may be these keep on varying, and with the agricultural practices also they will vary, but what I want to emphasize is that the total quantity available is 1555 million tons per year in India from various sources, agricultural residues which predominantly are rice and wheat straw, but there are other small categories which are available from industrial sources, from agricultural sources. Now, this all can provide you a potential raw material for solid biofuels, for liquid biofuels. Now, let us look at some of the issues of concern. The petroleum based liquid fuels are established sector of fuels. The major concern is the limited availability of crude compounded with increased demand. Demand is increasing, supply is limited, and you have to meet the gap. And that gap you need either alternative renewable sources of hydrocarbons. That means, again from it can be, I am giving you these options primarily which are from biological sources. There could be alternative purely from the chemical point of view, but from biological sources one could think of alternative sources of hydrocarbons. There are plants, many of maybe are aware, Euphorbiaceae species, many of the cacti type of plant, succulent plants have latex which is a mixture of hydrocarbons. Of course, there are limitations, there are practical difficulties to use them on a large scale, because their growth rates are very low, their productivities are very low, but still they provide you a theoretical option to look at. Second is microwave enhanced oil recovery, which is being processed to increase the yield of the petroleum from drilling. Microorganisms are used which produce certain surfactants in the oil wells, and thereby improve the release of the oil from the well. The second problem which can be solved by biological routes is eco-friendly processing of petroleum products. Many of the petroleum products which are low cost have problem of high sulfur content, high nitrogen content, heavy metals and wax, and these all contaminant in the crude give rise to pollutants while they are used, and they can be processed to remove the sulfur, nitrogen, heavy metals and wax using microbial processes, and if they are possible, if they are feasible, they can give rise to a very useful eco-friendly technology. Then you need many of the additives for improved performance. Many additives are added even in for petrol or diesel, just for improving the anti-wear and friction reduction, for combustion efficiency improving and reduced emissions. So, they all can be also processed using biological sources, but the main issue is alternative transport fuels. Now, alternative transport fuels can be ethanol is one candidate which has been talked about a lot. Again, I may add that ethanol is not a new molecule. Ethanol by fermentation has been produced since ages, both as a chemical feedstock as well as for potable purposes. The technology, the science, chemistry behind the same remains the same. The only thing is that now our requirement has added a new dimension, in which we need a different quality grade of alcohol, while in the for producing your as a industrial feedstock you are satisfied with 95% alcohol, for using in the fuel you need 99 plus percent alcohol. Water is not acceptable. Similarly, while in the case of beverages, of course, you had a still lighter problem, because you could use even 30, 40, 50, 60% alcohol, does not matter. And the second is biodiesel from non-edible vegetable oils. Many of the vegetable oils which are non-edible, tree borne, very often tree borne, which you do not find in our conventional practice a use for application, can be converted into biodiesel after transesterification, so that they get a mixture of. Now, this biodiesel they are produced from these vegetable oil, from the combustion point of view, has a very advantageous position, because in addition to carbon and hydrogen, they already contain a little of oxygen. They contain, because they are esters. So, they contain a little of oxygen, and whereby their combustion properties are superior than the conventional hydrocarbons. Then I think another area where biotechnology has made an impact is monitoring and abatement of pollution from petroleum sector. In the petroleum sector, for bioremediation of oil spills and oily sludge lands. Now, when the crude is transported, is bound to create pollution by spillovers and transportation material, and now to clear that, there is no other way excepting that you develop a bug which can eat it. And as a matter of fact, I think the first intellectual property debate in biotechnology started with that. And today we know that there are systems, including in India. I think the TERI has developed a system which is a consortium of microorganisms which can clear these oily sludges or petroleum spills effectively. And as a matter of fact, the technology they have transferred not only within India to variety of petrochemical companies, but even they have transferred it to many foreign petroleum companies. Treatment of petroleum processing effluents, again the problem is identical, because you need a microorganism which can grow on petroleum products, and biosensors for monitoring of pollutants. Particularly, as I mentioned that these pollutants which was mentioned in my earlier slides, for sulfur, nitrogen and heavy metals and wax content, you need to monitor them in the product stream, and thereby you can sense them, and different microorganisms can sense them easily. Now, I will take the first category of biofuel, ethanol from alternative feedstock. The conventional route for producing ethanol is molasses. I mean, for a variety of purposes, including in India, is molasses, which is a waste from sugar industry. I will not say waste, I will say a co-product, a co-byproduct from the sugar industry. Now, incidentally, this sugar industry waste or residue contains almost about 40 to 50% of sugar. Now, I will also like you to appreciate the point which brings out a difference between the biotechnology and chemical technology, that when we produce alcohol from this molasses, we get a concentration of about 8 to 10% alcohol, whereas and which is one of the highest product concentration in any bioprocess. I mean, you can rarely think of any other biological microbial process in which you have the concentration of the product as 8 to 10%. Ethanol is one of the glaring example, and which it produces, whereas in a chemical industry we have a residue or a waste which contains 50% sugar. I mean, that means in the chemical processing recoveries beyond this level are uneconomical, whereas biological processes can even make use of such lean resources. Another clear example, glaring example of this is bacterial leaching of mineral ores. Now, we have by conventional metallurgical processes, you can enrich, isolate the metal value from rich ores, but after the rich ores, the huge mounds of the lean ores which are left, you have no other choice excepting to go to bacterial leaching. So, I mean, one of the very glaring example of the biological systems is that they can use very lean resources. They are not dependent on, whereas chemical technology will often depend on very rich resources, pure sources, and then they can process. And ultimately, in any process, one day you are going to be depleted with the rich resources and left with the lean resources, and one has to depend upon. Now, here I have given you some alternative feedstock for producing alcohol, and these are the sources which are conventionally used, maybe in India, maybe outside India: sugar cane, sugar beet, molasses, potato, cassava. Now, the potato, cassava, sorghum and corn, they are primarily sources of starch, and the alcohol production is based on the starch content. The starch is hydrolyzed to glucose, and glucose is converted to the potential yield, crop yield in tons per hectare per year, and the alcohol yield liters per ton is given here. And essentially, the most important aspect is to look at the productivity of the alcohol liters per hectare per year. I mean, if I consider how much of crop I can raise in 1 hectare per year, and how much of, so these are the figures which indicate you the potential feature. Even now, sugarcane extends at the highest, and that was the reason why Brazil bent and took a decision to use sugarcane as a potential crop and not corn. Even if you see in the corn, the figures are much lower. Some of the alternative feedstocks that can be used for conversion to ethanol, as I mentioned, is a sugarcane juice, sweet sorghum juice, molasses, maua flowers. I mean, a limited resource, but has availability in a country like ours in the forest areas, and sugar beet. These are the pure sugar containing material, and they do not require much of pre-treatment. They can be fermented to ethanol directly by Saccharomyces cerevisiae yeast. I do not want to go in detail of the fermentation process. I am sure that all of you are familiar. The other are starch based: cereal grains, corn, sorghum, spoiled wheat, rice, and tubers, potato and cassava. All I gave you for some of these now the problem comes, the third category of feedstocks are lignocellulosic materials, the agricultural residue which I listed sometime a little ago. Now, most of these material, they have two major problems. One is that nature has not designed those residues for conversion to alcohol. They have been designed as structural material by their nature, and therefore, the nature has designed in such a way that you cannot make a dent on the structure, and in the process they have used another molecule along with cellulose, what we call as lignin, and these cellulose fibrils are interfaced along with lignin layers, and this lignin is a protecting layer for the cellulose molecule to be attacked by enzyme or acid or alkali, anything, and therefore, the cellulose, the lignin need to be removed before anything can be touched. Even after you have done the first part, lignin removal, and got a, let us say, purer cellulose material, even then there are many technological problems, and I have tried to summarize some of the technological problems in this equation. C6N denotes the cellulose, this is cellulose, N molecules of glucose, C6 sugar linked together in a linear chain. Now, this by enzymatic hydrolysis we convert into glucose or cellulose. This is C12 sugar cellulose, and this is glucose. Then these molecules can then go to alcohol by fermentation and carbon dioxide. The basic resistances that come in this job are essentially indicated here by A, B, C and D. A, the sugars, both sugars, glucose as well as cellulose, they inhibit the cellulase enzyme. They inhibit, they do not allow it to function beyond a particular point. Then the B, essentially the ethanol also inhibits the alcoholic fermentation as well as cellulose degradation, as well as the cellulase enzyme, alcohol also. And fourthly, the D, that is the accumulation of cellulose, reduces the yield of fermentable sugars. So, all these four put together results in a problem in the real issue that you cannot really convert conveniently the whole cellulose into ethanol. And I will show you some of the results. Now these are some of the studies, summary of the studies what we did in my laboratory. We have just attempted, first thing, these all results were done on sorghum bagasse. Probably all of you are familiar with sorghum, but we call it jowar, you know. Now there are number of varieties of jowar which have been developed in the country, and I took a variety which is called sweet sorghum, which doesn't produce much of grain, but it produces a stem like sugarcane, and which contains a juice of sugar. So, and then after extraction of the juice you get bagasse which is similar to sugarcane bagasse, and so I use that bagasse. In fact, by courtesy of IARI, I was provided the whole one plot material to me, which I crushed and used the bagasse fresh. So, what we did was, and again I took help of a kraft paper plant, because I did not do much study on the delignification part, because in the kraft paper manufacture they do delignification to remove the lignin, and pardon, they use soda, only soda. So, we used only your sodium hydroxide and carried out exactly in a small rotary digester. We carried out the whole process as per their details, and these were the kind of yields and results I have just summarized here in the pulp composition from sugarcane bagasse, and these are sorghum bagasse. You get slight differences, but obviously the composition will differ in natural products. So, you get those differences. Finally, I think the main step in the whole process remains enzyme production, and even today, although over the last I would say the history of this whole job started somewhere in early 70s. Since then, the cost of cellulose has drastically come down, productivities have gone up, but even today I can tell you the latest, the highest, the best figures which give Genencore in the US. In the last 10 years, they have reduced the cost, not 10 years, 5 years, they have reduced the cost of cellulose one tenth to 1/10. But even today, to make this cellulose hydrolysis feasible commercially, they need to reduce it by another to 1/4. So, this is the status. Even today, it is not economically viable. You have to bring down the cost of the enzyme to a level, so that you can make the sugar cost comparable with the cost of the sugar produced by sugarcane juice. Our sort of comparative platform is sugarcane juice, which is used industrially, which can be accepted. Now, our cost of processing has to meet the cost of sugar in sugarcane juice or sorghum juice, does not matter, but in the juice. So, the cellulose cost is a very big predominant parameter, which is going to play a key role, and people are trying. Now, here I have shown just by solid state fermentation a profile whereby the enzyme activity can be produced. Now, this profile shows the enzyme activity of the cellulase in terms of filter paper activity, and this is the beta glucosidase activity. Now, in this enzyme preparation, essentially beta glucose cellulase enzyme is a multi enzyme complex. It is not a single enzyme. It has at least 3 to 4 enzyme components, in which the beta glucosidase activity is a limiting factor. As I think you recall my earlier slide, sorry, I have shown accumulation of cellubiose reduces the yield of fermentable sugars, that inhibits the cellulose hydrolysis. So, if the beta glucosidase is low, it will not allow it will accumulate cellubiose, which will reduce the cellulose hydrolysis. So, this is essentially therefore becomes a limiting factor. Then of course, this was the production of cellulase in submerged fermentation, earlier it was by solid state fermentation. Now, this is by submerged fermentation, in which the soluble proteins, filter paper activity and beta glucosidase is shown here. Here also beta glucosidase is the limiting factor. So, we try to produce beta glucosidase by Aspergillus pentai, another fungus, and this enzyme, this beta glucosidase was supplemented to the trichoderma cellulase, and a mixture was used to arrive at the final optimum mixed enzyme level. Then it was used in a packed bed reactor for conversion of the bagasse pulp. I am saying it is a delignified pulp to ethanol, and both the hydrolysis and fermentation to the same vessel a yeast was added. Yeast was pre-grown in a separate vessel and added. The concentrations are given here. Solid to liquid ratio is 1:5. Liquid, I mean the enzyme solution, the enzyme crude enzyme preparation. Cellulose was of the order of about 8 units per gram of cellulose. Yeast was 50 milligrams per gram of cellulose and temperature of 30 to 35 degree centigrade. Now, essentially now here what we noticed was that this optimum temperature of the yeast was also a limiting factor. Was very often the cellulase action is optimum at 45 to 48 degree centigrade, 50 degree centigrade. Yeast productivity becomes 0 beyond 35. I mean optimum is 30, but at up to 35 it can tolerate, but beyond 35 degree centigrade the viability of the yeast goes down with no ethanol fermentation. So, this was another problem area, and so either you can optimize for yeast or for cellulose hydrolysis. If you compromise on that, other will suffer. So, what we did, we contacted IMTEC in Chandigarh. They had a yeast strain which was thermotolerant, and it was able to maintain viability up to 39 degree centigrade, not 30, 35, 39 degree. It was a little better. So, we could operate our fermentation, our whole reactor not at 30, but at 38. We operated 38, and the profile of this fermentation at these conditions, FPA 8 units per gram pulp, solid to liquid as 1.8, which was the maximum best performance we could get, was here, and we could not get alcohol more than 3.8 to 3.9%, as against 8 to 10% in the classical sugar fermentation. Now, obviously, this process even today till to date in our sort of cost estimation is still far from expectation from the commercial point of view, from the economic point of view. Technically, yes, we can demonstrate, there is no problem. We had designed the whole process, we had operated the whole plant, whole process in this format, where we had 2 alternative columns, and the enzyme was used in the first column, dissolved, almost about 75% enzyme was recovered, reused in the second column. So, the every time the enzyme addition was not 100%, it was only 25%. So, what I showed earlier, the FPU 8 IU per gram essentially is 2 IU per gram, because 75% can be recovered and reused. And this is the yeast growth cycle. Here we have the pulping cycle, and deep dignified pulp is added into these 2 columns, spent solids, and the mixed enzyme is recycled back, and you have fermented broth. Now, this fermented broth we could get maximum 3.8 to 4%, not beyond. That was the best condition we could achieve, and to my knowledge even in other places they have not produced any better than that. Now, let us come to, of course, the story behind after this is downstream processing, where we have to distill it out, or by recovery processes we have to get a 99% plus alcohol. Now, that part remains the same, whether you produce from sugarcane or you produce from bagasse, makes no difference. The other liquid biofuel is biodiesel, which has been talked about a lot in current scenario. And if you look at the definition, there are essentially the alkyl esters of vegetable oil fatty acids derived from non-edible tree borne oil seeds as a diesel substitute. The process essentially requires the availability of stable and efficient lipases. If you want to use a biological route, there are 2 routes which can be used for this. Again, you can produce this chemically by using acid or alkali catalyst, methoxide, sodium methoxide, or any other catalyst, or even you can use lipases. Of course, most of the processes that are being run today are essentially based on alkali catalyst. Enzyme catalyst processes are still a matter of sort of investigation, and you require the transesterification. Now, this is less polluting. I mentioned also biodiesel has an advantage, two advantages. One is on the combustion part, it is superior than the diesel derived from crude, mainly because of a small content of oxygen being present there. So, it undergoes combustion more efficiently than the normal diesel. And second thing, the biodiesel production can be managed even in a sustainable manner, even on a small scale. So, it can meet very often our rural requirement and in a sustainable manner. You do not need a very large scale petroleum refining plants to produce that, even on a small scale it is feasible, because it can use the crops. It is considered biodegradable and non toxic, does not produce any of the toxic residues or any other problems. The development of biodiesel industry will strengthen the domestic rural and agricultural economy. It will also help to develop the agricultural economy. Also, the biodiesel has positive energy balance ratio. By energy balance ratio, I mean the energy consumed in the cultivation of the oil to that generated by conversion into biodiesel. It has a positive ratio. Biodiesel and biodiesel blends can be used in all types of engines without or with minimum modification. As a matter of fact, the extreme can be people have used the triglycerides in the pure form without even transesterification in engines. Of course, the only problem is the engine life goes down, the cleaning required is very frequent, but otherwise you can use even vegetable oil as a source of fuel, but it is not favorable with the engine. And if you convert that into esters, the alkyl esters, the engine can accept as it accepts the diesel. So, the biodiesel has been experimented in different countries. The sources which have been used in different countries are listed here. In India, of course, we are mainly looking at Jatropha as a source. Now, Jatropha essentially has a unique feature compared to other sources of vegetable oil, in that it is a very sturdy plant, does not require very strong, very good quality of soil, is not the irrigated soil, it can manage on the rain fed areas, water requirement is very low, the cycling time is very fast, and the most important advantage is, from the Indian point of view, the cattle do not graze it. Cattle do not graze it. So, even people can use it for fencing purposes and protecting their agricultural crops. Now, of course, it is non edible in the sense that it contains some toxic component and is not acceptable, as because the edible oils essentially also goes from the point of view of the conventions. I mean it is a very difficult statement to make non edible. What is non edible? Take for example, mustard oil, which is a predominantly used oil in Bengal and Orissa, including UP, but probably in South India, Andhra Pradesh or Tamil Nadu, they will rate it as non edible. I mean they will not be able to smell it even forget about eating, but in Bengal and Orissa, it is a very acceptable oil. So, it is a very difficult to say non edible, but again I like to specify that we take into that spirit. It is not a very popular thing which has been accepted, and Jatropha curcus plant can grow almost anywhere, even on gravelly, sandy or saline soils. So, all inferior quality of soils can be readily used for plantation. It is an hardy and any special requirement with reference to climate and soil, grows rapidly, hardy to dry weather conditions, and not browsed by goat and cattle. If you look at the energetics, we made some energetics scenario in my laboratory itself. One of my students did it. An energy balance ratio is a comparison of energy stored in a fuel to the energy required to grow, process and distribute that fuel, and the balance ratio comes to 2.5 to 1. That means, the energy output by consuming biodiesel as a source of energy is 2.5 to 1 consumed in growing the plant, converting into biodiesel and distributing it. Of course, even if with a sort of a error of let us say plus minus 10-20%, even this is favorable. I will not claim that I will take this figure with a pinch of salt, and but even then the ratio is positive, it is not in the negative direction. These are typical Jatropha plantations from the nursery, seeds and the dried seeds, the green seeds and the dried seed. It is a beautiful, in fact, as a matter of fact, I personally have in my house, it is an ornamental plant, it looks beautiful. It is an ornamental plant, Jatropha plant bearing the seeds, and the seeds are housed in a cover. The conversion of triglyceride to biodiesel follows this kind of a stoichiometry almost 1:1 on weight basis. 1 ton of tristyrene can give you almost 1 ton of alkyl ester. So, as a matter of fact, roughly I mean just I am taking 890 and 894 as equal, and you get almost a stoichiometric yield 1 ton to 1 ton, 1 ton oil, 1 ton biodiesel. Glycerol is obtained as a byproduct, because from the ester the glycerol is removed and replaced by alkyl group. You can use variety of feedstocks, variety of catalyst. It is just a sequence of steps which are involved in producing biodiesel from Jatropha oil. Now, the problem what are the problem areas again, because I wanted to concentrate more on the commercial problem areas. Most of us are familiar, I mean there are number of institutions in the country which have working on the technology for converting, and in my opinion today if I assess the whole scenario, there is not much problem in converting triglycerides to biodiesel, hardly any problem. There are a lot of developments, there is no problem. The essential problem lies in identifying a feedstock. Essential problem is a feedstock, and I think the problem is agrotechnology for feedstock. When I say agrotechnology, I am referring to a reproducible technology with a sustainable yield of oil. Not like that 1 year you produce let us say oil seeds containing 40% oil, next year it comes down to 15%. Somebody who has put a commercial plant will poor fellow drown. So, I am referring to an established consistently reproducible feedstock. Integration of biodiesel and bioethanol as a total green technology. Another issue is which I personally feel very pertinent is, at the moment we are all talking about vegetable oil, methanol as the alcohol for alkyl esterification. Now, methanol is not a green fuel, green molecule. Instead of that, you can use even ethanol. Ethanol can be produced also by biological route. So, if you have the whole process which is green as a total green technology, ethanol can be concentrated more to provide a green technology. Then finally, I think the one of the major limiting factor will be utilization of the bioproducts, and bioproducts are oilseed cake and glycerol. Essentially, unless we have established a remunerative application for these feedstocks, these byproducts, like for example, even today oilseed cake is not edible for cattle purposes. It contains some toxic compounds for which it is not fed to the cattle. So, we need to modify it or produce some other product. I mean whatever, there are many options available. If we can make it a industrially useful feedstock which can fetch some value, your whole technology can become economically viable, because ultimately what my objective of utilization of byproduct is that you should be able to recover the cost of oil seeds, cost of oil from the byproducts. Then you can really meet with the and then finally, I think a very important factor is an assured roadmap for consumption of biodiesel. You see, CNG did not become a viable route for fuel in India unless the government took a decision that okay, in Delhi we will have the whole fleet of taxis and auto rickshaws and buses run on CNG. So, you need an assured roadmap for consumption of biodiesel. Somebody will produce biodiesel, and if there are no takers, it will flop. And I think there is a possibility, there is a very for example, even state transport city buses fleets can run on biodiesel. If I know, I have seen myself in Austria, in Graz, the whole city bus in the Graz city is on biodiesel fleet, and just like we have CNG in Delhi, they have biodiesel in Graz. So, I think there is an assured requirement which can meet the industrial, which can develop the industrial confidence. Railways is another area, defense is another area, the major consumer of diesel in their trucks and all of that, and then taxis of course. So, I think one has to have an assured roadmap, unless there is a policy on that. So far there is no policy. The only policy we have got two things, one is the cost of biodiesel is issued by the government, and other is specifications, but application factor which we have so far established no norms, and those norms are required for a assured commercial viability. Again, this graph shows essentially that the whole biodiesel feasibility production cost is dependent on oil content and the cost of seeds, and somewhere here is our tie line, where that means, or essentially what it means, that you need anything less than 20% oil content, or sorry, anything less than 20 rupees a liter, anything more than 20 rupees a liter of oil is not feasible to be used for biodiesel production, and which will require essentially a content of for different oil content, the cost which can offer, which you can offer for the oil seeds is different. For example, if we take 30% oil content, you can offer about, let us say 2.5 rupees per kg. So, similarly, I mean the whole oil content, the seed, I mean the biodiesel cost, they are all linked together, and you have to have, when you consider a commercial proposition, they have all to be linked. But the problem lies today, a major problem that lies today, that there is a very large variation in the oil content. In many of the experimental situations, the oil content over generations has varied. The first crop and second crop and third crop, it has changed. You start from a light crop, ultimately you end up lower, which probably is going to be a very serious problem. And as a matter of fact, I will come down maybe towards the end to provide some potential solution, although it is not yet established. Now, feasibility will be affected, as I mentioned, by price of crude oil, which of course is in favor, is growing very fast. So, it will, the higher it goes, it will support the feasibility of biodiesel, and I think by now it has already become, even at 98, it is fairly feasible. I think another factor which can affect is carbon trading. Now, after the Kyoto Protocol, when we have the provision of carbon trading, where the reduction in the greenhouse gases can fetch you some benefits, one can make use of those opportunities in production of biodiesel. Percentage oil in seeds. Another feature is probably intercropping. You can intercrop the biodiesel, the oil plant, triglyceride plantation with another economical plant like stevia or some omega 3 containing oil. You can put a intercropping, you can manage, I mean ultimate purpose is to make a economic balance. In fact, I am not in favor to consider that all our wasteland will be used for Jatropha personally, because wasteland again is not a really wasteland. Wasteland has lot of requirement in a social perspective, and we should not diminish that. Just like somebody saying that okay, we will clear all our forest land, which is not feasible. Forest has a social requirement. Similarly, wasteland also has a requirement. Going below a particular percentage will be ecologically non-viable, not sustainable, and yield of course 1 ton to 10 ton per hectare is the requirement which probably will require. This is something to give you illustrate the point of clean development mechanism. For the principle basically is that by there is an agreement between the developed countries and developing countries under the banner of UN, that while developed countries will not increase their greenhouse gases, but they will not be forced to reduce it, but they can buy carbon credits from the developing countries if they take initiatives to reduce the greenhouse gases and thereby support their growth, industrial growth, and the industrialized countries can buy credits and developing countries can create new credits in projects such as biodiesel. And in many cases even the non economical projects purely on commercial basis might come out to be economically feasible. Now, essentially finally what I wanted to say, the future in my opinion for biodiesel will lie on looking at the alternative sources of lipids oils. And in my opinion microalgae and microorganisms, other microorganisms are likely to be a major supplier of oil if biodiesel has to come in place. Algal cultivation, which again requires photosynthetic mechanism to produce, and there are organisms which can accumulate almost about 50 to 60% of their weight, dry weight as oil, need to be cultivated, and they can be the potential source of. Similarly, some of the yeast can be cultivated to produce oil and as a feedstock for, because mainly because their mass cultivation is feasible. You are not dependent on land, and harvesting and transporting costs are relatively low. You can have your the processing units in close proximity to the biodiesel facility, which is feasible, whereas in the case of let us say product like Jatropha, it is not feasible. You have to grow at different places, you have to transport all that, but in the case of if you produce let us say microalgae or yeast, it is possible to put their plantation in close proximity of the processing units, can facilitate reduction of greenhouse gases so as to attract the carbon credits. The cultivation of lactophareous plants such as Euphorbiaceae, Sapotaceae, of course, again it has been tried a lot, but is still not economically viable. But this they can be probably looked at in some specific geographical locations using regio-specific species. They can be considered, and of course, you can develop tissue culture, mass propagation, agrotechnology for these products. Thank you very much for your kind attention.